Scientists thought they understood the beginning of everything. Then James Webb sent back a signal that shouldn't exist. Webb found a galaxy already carrying oxygen, an element that requires multiple generations of dead stars to even create, existing when the universe was barely 290 million years old. Something was there before it had the right to be. Then detectors picked up a signal. Not light, not radio, something older. A frequency humming through space-time itself, from a place our physics says is completely unreachable, from before the Big Bang ever happened. By the end of tonight, you will know exactly what that signal is, and why it means the Big Bang was never really the beginning. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. Something was wrong with the data. Not slightly wrong, not within the margin of error. Wrong in the kind of way that makes scientists go quiet, recheck their instruments, recheck their math, and then go quiet again. The James Webb Space Telescope had been staring at a single point in the sky, a faint smear of ancient light, for nearly 10 hours. Not 10 minutes, 10 hours. Webb's near-spec instrument, the most powerful spectrograph ever placed in space, was doing what it does better than anything humanity has ever built, pulling apart the light from the farthest reaches of the observable universe and reading it like a fingerprint, pulling out its chemical composition, its temperature, its distance, its story. What the data said should not have been possible. Let me explain what Webb was actually measuring, because the number it returned is the key to everything. When light travels across an expanding universe, the expansion itself stretches it. The farther the light travels, the more it stretches, shifting it toward the red end of the spectrum. Astronomers call this redshift. Think of it like the sound of a train moving away from you. The pitch drops, the sound stretches out. Light does the same thing across cosmic distances, and the higher the redshift number, the farther the light has traveled, which means the further back in time we are looking. Webb measured the redshift of this galaxy candidate at 14.32. To understand what that number means, the universe today is approximately 13.8 billion years old. At a redshift of 14.32, we are looking back to a time when the universe was only 290 million years old. That is roughly 2% of the universe's current age. If the entire history of the cosmos were compressed into a single calendar year, this galaxy existed in the second week of January. The galaxy's name is JWST 14, and the confirmation Webb provided was not a rough estimate, not a best guess from a faint smudge of light. Scientists confirmed it spectroscopically, meaning they analyzed the precise chemical fingerprint of its light with an instrument sensitive enough to identify individual elements across billions of light years. Spectroscopic confirmation is the gold standard in astronomy. No ambiguity, no alternative reading. This galaxy was real, and it was sitting in a moment of cosmic time where, according to our best models, it had absolutely no right to exist in the form it took. The size of it was the first problem. JWST 14 spans over 1,600 light-years across. Our own Milky Way galaxy is roughly 100,000 light-years in diameter, so this ancient galaxy is far smaller than ours. But that comparison misses the point entirely. The point is that at 290 million years old, a galaxy of this scale should not have had nearly enough time to form. Galaxy formation is not an instant process. Gravity must pull vast clouds of gas together over immense timescales, triggering star formation. Those stars must live and die. Their remnants must collapse and seed the next generation. The process is slow by design, written into the physics of how matter behaves. Our best model of cosmology, called lambda CDM, which describes how dark matter, ordinary matter, and dark energy interact to build the universe's structure over time, predicts that the very early universe should contain only small, irregular, primitive galactic structures. Patchy, dim, disorganized, the raw ingredients of something, not something fully assembled. JWST 14.0 was none of those things. Webb found a galaxy dominated by young stars, thousands of them, spread across more than 1,000 light-years, not the signature of a single hungry black hole making the galaxy appear artificially bright. Real stars, real mass, a real, structured galaxy, already mature in a universe that was barely learning to exist. That alone was difficult to explain. Then came the oxygen. Oxygen is not a simple element. Unlike hydrogen and helium, the two lightest elements forged in the first minutes after the Big Bang, oxygen has to be built. Stars spend their lives fusing lighter elements into heavier ones deep in their cores. When massive stars exhaust their fuel, they explode in supernovae, scattering those heavier elements into the surrounding gas. The next generation of stars forms from that enriched cloud. Then that generation dies, enriching it further still. For oxygen to appear in measurable quantities, this cycle must have already run its course multiple times. In March 2025, the ALMA telescope, the Atacama Large Millimeter Array, a network of 66 high-precision radio antennas nestled in the Chilean desert at an altitude of 5 kilometers, roughly 16,000 feet, confirmed oxygen emission signatures in JWST 14.0. This was the earliest detection of oxygen ever recorded in the history of human observation. Oxygen, in a galaxy that had existed for only 290 million years. Think carefully about what that timeline requires. For oxygen to be present in detectable amounts, multiple generations of massive stars must have already been born, lived full lives burning through their fuel in millions of years, and died in spectacular explosions, all within a cosmic window so narrow that by the standard models, there was barely room for the very first generation to have formed at all. Scientists had no clean explanation, not a partial one, not a working hypothesis with a clear path forward. They had a finding that genuinely strained the boundaries of the best cosmological framework humanity has ever constructed. And then, within a year, the record broke again. In May 2025, a second galaxy was confirmed, designated MOMZ-14, redshift 14.44, even more distant, even earlier in cosmic time, even more chemically evolved than it had any right to be. The most distant confirmed galaxy in human history had held its record for under a year. A new one had already surpassed it. 2 galaxies, both impossibly structured, both chemically mature, both sitting in an era when nothing like them should have existed. The models were not slightly off, dramatically off. Cosmologist Michael Boylan Colchin, based at the University of Texas at Austin, stated it plainly. Findings like these require, in his words, something very new about galaxy formation or cosmology. Not a minor adjustment, not a recalibration of a single parameter. Something genuinely new. That phrase carries weight. Cosmology does not invite those words lightly. The Lambda-CDM model has survived decades of precision testing, radio surveys, supernova measurements, the detailed mapping of the cosmic microwave background. It is not a guess. It is a deeply tested, mathematically robust description of how the universe grows structure over time, and Webb's early galaxies are stressing it in ways it was not built to accommodate. Some researchers are exploring whether the first stars formed faster and more efficiently than the models assumed, burning through their fuel so rapidly that they seeded heavy elements earlier than predicted. Others suggest that early galaxies may have operated under different physical feedback mechanisms, allowing growth to accelerate in ways the current framework does not capture. Both ideas are being actively investigated. Neither has yet provided a complete answer. The debate is alive, unresolved, and, for the first time in a long time, genuinely urgent. But JWST 14.0 and MOMZ-14 were not the only signals arriving. And this is where the story deepens in a way that no single telescope, no single branch of science can explain on its own. In June 2023, while Webb was still building its case from galaxy to galaxy, a completely separate branch of astronomy delivered its own announcement, using completely different instruments, measuring something that light cannot carry at all. The NanoGrav collaboration, the North American Nanohertz Observatory for Gravitational Waves, released the results of 15 years of continuous observation, 15 years of data gathered by timing the pulses of millisecond pulsars scattered across our galaxy. Pulsars are the collapsed remnants of dead massive stars, spinning at extraordinary speeds, emitting beams of radio waves with a regularity that rivals atomic clocks. When a gravitational wave, a ripple in the fabric of space-time itself, passes between us and a pulsar, it introduces a tiny but measurable shift in the arrival time of those pulses. NanoGrav had been collecting and studying those shifts for a decade and a half across dozens of pulsars simultaneously. What they found was a stochastic gravitational wave background, a background hum of gravitational waves washing through all of space-time simultaneously from every direction at once. Not a single event, not a single source. A continuous, omnidirectional vibration embedded in the very geometry of the universe. And simultaneously, independently, 3 other global collaborations confirmed the same signal: the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array. 4 separate datasets, 4 independent teams. One result: the signal hums at approximately 32 nanohertz, a frequency so impossibly low it falls entirely outside any range human senses could detect. The lowest pipe organ note ever heard sits trillions of times higher in frequency than this. The individual waves in this background take years, possibly decades, to complete a single oscillation. And they are passing through you right now, through the walls surrounding you, through the ground beneath your feet, silently and constantly, altering the geometry of space by amounts so vanishingly small that only the most precise timing instruments on Earth can register them at all. The leading explanation points to supermassive black hole binaries, pairs of black holes, each potentially billions of times the mass of our Sun, slowly orbiting each other at the centers of ancient merging galaxies across the universe's history, gradually spiraling inward and radiating gravitational energy as they go. Almost certainly millions of such pairs are scattered across the cosmos, and their combined output could produce exactly this kind of low background hum. But that explanation is not settled, and what remains unresolved is the part that matters most. Some physicists believe the signal carries a component that black hole binaries alone cannot account for, one that may trace back to processes in the very early universe, from the first fractions of a second after the Big Bang, or from something that preceded it entirely. Several early universe models, covering cosmological phase transitions, primordial inflation, and phenomena that current physics can describe mathematically, but has never directly observed, predict gravitational wave signatures that would appear indistinguishable from what NanoGrav measured. The data cannot yet separate those explanations, and that gap in our understanding is not a small one. And then there is a third signal, one that has been sitting in the data for decades, quietly refusing to go away regardless of how carefully scientists reanalyze it. The cosmic microwave background, the CMB, is the oldest light in the observable universe. Produced approximately 380,000 years after the Big Bang, when the infant universe finally cooled enough for electrons and protons to combine into neutral atoms and release light for the first time, this ancient glow has been traveling through space ever since, cooling as the universe expanded, fading into the microwave range, until today it fills the entire sky with a faint, uniform warmth carrying the imprint of the universe's earliest conditions, a photograph taken when the cosmos was newborn. ESA's Planck satellite mapped that ancient light to the highest precision ever achieved. And within that map, within the oldest image any telescope will ever capture, 4 large-scale anomalies persist. A hemispherical asymmetry where one half of the sky carries measurably more CMB power than the other. A cold spot in the southern hemisphere, far larger and colder than any random fluctuation in the standard model predicts should exist. A suspicious alignment of large-scale structural features with the plane of our own solar system. An alignment so unexpected it was given the name the axis of evil in a peer-reviewed scientific paper. And a missing correlation in temperature across large angular scales that the models clearly predict should be present, and simply is not. Each anomaly sits at a level of statistical significance that makes dismissal uncomfortable. All 4 persisting simultaneously, confirmed in both the Planck dataset and the earlier WMAP satellite data, is something the standard model has no ready answer for. 3 independent lines of observation, 3 completely separate branches of science, using completely different instruments, measuring completely different phenomena, and all 3 pointing, from different angles through different methods across different timescales, toward the same region of cosmic history, the era before our universe's visible boundary. None of these findings in isolation demands that physics be rewritten. Each one has proposed explanations, or at least proposed modifications to existing frameworks. But together they create something harder to dismiss: a convergence. 3 separate instruments pointing at the same blank space on the map of what we know, and that blank space has an edge, a hard boundary, a wall. Webb cannot see beyond that boundary. No telescope built from glass and metal and photon detectors ever will. The oldest light in the universe is, by definition, the oldest light, and beyond it lies an era that electromagnetic signals of any kind cannot carry information out of. A wall stands at the edge of everything our cameras and spectrographs and infrared sensors can ever reach. For a long time, that wall was considered absolute, the final horizon, the permanent limit of human knowledge about what came before. But one of the 3 signals we just encountered travels by an entirely different set of rules. It does not travel as light. Light cannot carry it. Nothing about the barrier that stops light applies to it. And that single fact changes everything about what might actually be possible. That barrier has a name, and understanding it changes everything. Not just what we can see, not just how far our telescopes can reach, what we can ever, in principle, know about the universe we live in, and what came before it. Most people assume that with enough technology, a powerful enough telescope, a sufficiently sensitive instrument pointed at the right patch of sky, we could eventually see all the way back to the beginning. Keep building better tools, the thinking goes, and the darkness retreats. The universe opens, the mystery yields. That assumption is wrong, and the reason it is wrong is one of the most profound physical facts in all of science. Let's talk about the oldest light in existence. Approximately 380,000 years after the Big Bang, the universe reached a turning point. Before that moment, all of space was filled with an ionized plasma, so dense and so energetically violent that light could not travel more than a fraction of a millimeter before colliding with a particle and being scattered back. Imagine trying to shine a flashlight through a wall of solid fog so thick that the beam vanishes the instant it leaves the lens. That was the early universe, scaled to encompass all of reality. No photon, no particle of light could travel freely through it. The cosmos was, in every meaningful sense, opaque. Then, as the universe expanded, it cooled to the point where electrons and protons could finally combine into neutral hydrogen atoms for the first time. And the moment that happened, the fog lifted. Light, which had been trapped, scattered, unable to move, suddenly had a universe to travel through. It flooded outward in all directions simultaneously, from every point in space at once, carrying the thermal imprint of that first moment of transparency. That light is still traveling, still arriving. Right now, from every direction in the sky simultaneously, the afterglow of that ancient moment is washing over us, cooled by 13.5 billion years of cosmic expansion, from a searing plasma glow to a faint whisper of microwave radiation, invisible to the naked eye, detectable only with sensitive radio instruments. We call it the Cosmic Microwave Background, the CMB, the oldest image the universe has ever produced. And it is a wall, not a wall in the sense of something solid, a wall in the sense of a permanent, physics-enforced horizon, the absolute limit of what any telescope using light can ever observe. Let's be precise about what that means. The James Webb Space Telescope observes in near and mid-infrared light, wavelengths just beyond what human eyes can detect, stretching into the faint heat glow region of the spectrum. Webb is the deepest infrared instrument humanity has ever placed in space, orbiting nearly 1.5 million kilometers, roughly 930,000 miles, from Earth at a point called the second Lagrange point, a gravitational sweet spot that lets it remain stable and cold and perpetually facing deep space. With its 6.5-meter gold-plated mirror, the size of a two-story building laid on its side, Webb collects light that has been traveling for over 13 billion years, and even Webb cannot see through the CMB. No telescope can. Not because we lack the engineering, not because the mirror is too small or the sensors too crude or the orbit too noisy, but because the plasma that existed before 380,000 years after the Big Bang physically scattered and absorbed all electromagnetic signals of every wavelength. Infrared, radio, ultraviolet, X-ray. The barrier stops all of them equally. Every galaxy Webb has ever found, JD's GSZ 14-0, MOMZ 14, the massive early galaxies researchers have nicknamed the red monsters for their unexpected brightness and density. Every single one of them sits on this side of the wall, the post-plasma side. The era after light was first set free. They push our models hard. They challenge our understanding of how structure forms in the early universe. But they cannot show us what came before them. The wall sits between us and that era, and no improvement in optics will change that. Think of it this way. The CMB is not a distant object. Webb hasn't quite reached yet, like a mountain range still visible on the horizon. It is more like the surface of frosted glass surrounding us on every side, and beyond that glass, every record of what happened has been thermally erased and scattered. Whatever. Information existed from before 380,000 years after the Big Bang has been, in terms of light, permanently destroyed by the plasma that surrounded it. That is not a temporary limitation of science. That is the permanent boundary of what electromagnetic observation can ever know. But here is where the story cracks open, because the wall is not entirely featureless. The CMB is not a perfect, uniform glow. When ESA's Planck satellite mapped it to the highest precision ever achieved, spending 4.5 years measuring temperature variations across the entire sky down to differences of 100,000th of a degree, it revealed something deeply unsettling. 4 large-scale anomalies embedded in the oldest light in existence that the standard model of cosmology cannot explain. One half of the sky carries measurably more CMB power than the other, a hemispherical asymmetry so pronounced it held up across both the earlier WMAP satellite data and the far more precise Planck measurements. The universe should look statistically the same in all directions. At these scales, it does not. A region in the southern hemisphere runs dramatically colder than any standard model prediction allows. A cold spot roughly 10 degrees across in the sky, larger than 20 full moons placed side by side, far below the temperature range that ordinary random fluctuation could produce. Researchers have tested this extensively. The cold spot persists. 2 large-scale structural features of the CMB, what physicists call the quadrupole and the octopole, align suspiciously with the plane of our own solar system in a pattern so unexpected that a peer-reviewed paper published in 2005 gave it a name: the axis of evil. A name chosen not for drama, but because an alignment this specific with the plane of our own tiny solar system, embedded in the oldest light in the universe, should be physically impossible if the CMB truly reflects a random isotropic distribution. And at angular scales above 60 degrees, the large-scale temperature correlations that every simulation of the early universe predicts should be visible, the signal simply goes quiet. The correlation is missing, not reduced, missing. Each of these anomalies, taken alone, sits at a statistical significance that makes casual dismissal difficult. All four persisting simultaneously across two independent satellite datasets, separated by years of technological improvement. That is something science has not resolved and has not been able to explain away. Some physicists believe these patterns are imprints, not of processes that happened after the Big Bang, but of conditions that existed before the plasma era, before the wall, when whatever was happening in the universe left an impression so deep that it survived through the formation of the CMB itself and remained encoded in the oldest light we can observe, like a watermark pressed into paper before the ink ever dried. That is a profound and uncomfortable idea. Here is the paradox at the center of everything. The CMB is the oldest image in existence. No telescope using light can ever see beyond it. That boundary is not theoretical. It is written into the fundamental behavior of electromagnetic radiation. We accept this. We work within it. But embedded in that oldest image are four patterns that our best models cannot explain. Patterns that some serious, peer-reviewed physicists believe were placed there by something that happened before the image itself was created. The wall is real. The information from before the wall should be gone, permanently erased by the plasma that preceded it, and yet the wall itself appears to carry marks that should not be there. So, either the standard model is missing something profound about the processes that shape the early universe, or those marks are genuinely older than the light that carries them. Either answer shatters something. But there is a third path through this paradox, and it was hiding in plain sight in the nanograv announcement. Gravitational waves are not electromagnetic signals. Light is a disturbance in electric and magnetic fields. Gravitational waves are something categorically different. They are disturbances in the geometry of space-time itself, a ripple in the actual fabric of space, propagating outward from whatever generated it, compressing and stretching the distances between objects by amounts so small they make a single atom look enormous by comparison. And because gravitational waves are not electromagnetic, because they do not interact with charged particles the way light does, the plasma that made the early universe opaque to all electromagnetic signals has no effect on them whatsoever. None. Picture the CMB barrier as a wall of solid stone, absolutely impenetrable to anything carried by light or radio or X-ray. Gravitational waves pass through it the way sound passes through a wall. A different medium, a different mechanism, a different set of rules entirely. The stone that blocks your vision cannot stop the vibration. This means that gravitational waves generated before 380,000 years after the Big Bang, in the first fractions of a second of cosmic history, could, in principle, have travelled through the plasma era unchanged, crossed the barrier that stops all light, and continued propagating outward through 13.5 billion years of expanding space until they arrive here, now, detectable by instruments sensitive enough to read them. And if something generated gravitational waves before the Big Bang itself, in whatever state of existence preceded the moment our universe began, those waves would face no barrier at all, no wall, no plasma, no horizon. They would simply travel, unimpeded, through whatever followed. The nanograv background, that omnidirectional hum confirmed simultaneously by 4 independent global collaborations is real. Its most likely explanation involves supermassive black hole pairs spiraling toward merger across the universe's history. But that explanation has not fully closed the question. Some component of that signal may trace to processes earlier than any black hole could have produced, processes in the first instance after the Big Bang, or before it. We do not yet know which. The data cannot yet distinguish between these possibilities with certainty, but the signal is there, and it travels in the only language that can cross the wall, so the wall is real. The electromagnetic horizon is permanent. The oldest light we can ever observe is the CMB, and it is already riddled with patterns our best model cannot explain. But gravitational waves cross it freely. They have been crossing it since the moment they were generated, whenever and wherever that was, and we have just confirmed, with 15 years of pulsar timing data from 4 continents, that a background of them is humming through all of spacetime right now. The question is no longer whether a signal could theoretically cross from before the visible boundary of our universe. The question is whether the signal we are already measuring, the one already in the data, contains an echo of something that happened on the other side. And to understand what could generate a signal like that, we need to understand something we have been quietly avoiding until now. Something our equations have pointed toward for over a century, and something physics has never been able to look directly in the eye. What actually happened at the moment the universe began? Gravitational waves are not a new idea. They are not a recent hypothesis born from the pressure of anomalous data. They are more than a century old, predicted with mathematical precision by a man sitting at a desk in Berlin in 1916, working from nothing but geometry and logic and an almost unreasonable confidence that the universe behaved according to rules that human minds could discover. Albert Einstein published his general theory of relativity that year, and embedded within its equations, almost as a side consequence, a mathematical ghost the physics itself could not avoid producing, was the prediction that accelerating masses would send ripples through the fabric of space-time. Waves. Not sound waves moving through air, not light waves moving through electromagnetic fields, but distortions in the structure of space and time themselves, spreading outward at the speed of light from whatever violent event created them. Einstein himself doubted they would ever be detected. The distortions they produce are almost incomprehensibly small. He was wrong about that, but it would take 99 years to prove it. To understand why gravitational waves matter so profoundly to the question we are carrying, we need to understand what they actually are, not just what they are called. General relativity describes gravity not as a force, the way we intuitively experience it, but as a curvature in the 4-dimensional fabric of space-time. Mass bends the space around it. Other objects moving through that curved space follow the bends, and we experience that following as gravity. The Earth curves space. The Moon follows that curve. We stand on the Earth's surface because the geometry of space beneath our feet curves inward, and we are simply resting at the bottom of that curve. Now picture 2 extraordinarily massive objects, 2 black holes, each with a mass of tens or hundreds of suns, locked in orbit around each other, spiraling closer and closer over millions of years, moving at a significant fraction of the speed of light. As they orbit, they don't just sit still in space, they churn it. They distort the space-time fabric around them with every rotation, sending ripples propagating outward in all directions, like 2 stones dropped simultaneously into still water, creating overlapping rings that spread to every shore. Those rings in the water analogy are mechanical. They need water to move through. Gravitational waves need nothing. They are not a disturbance in any medium. They are a disturbance in the medium itself, in space-time, and they propagate through the complete absence of anything, through perfect vacuum, through the opaque plasma of the early universe, through walls of any material ever conceived. Nothing stops them, because nothing is what they travel through. That is not a poetic description. That is the physics. For nearly a century after Einstein's prediction, gravitational waves remained theoretical, beautiful mathematics, untouchable reality. Then, on the 14th of September 2015, at 5:51 in the morning Eastern Time, two detectors operated by the LIGO collaboration, the Laser Interferometer, Gravitational Wave Observatory, with facilities located in Hanford, Washington and Livingston, Louisiana, registered a signal lasting approximately 0.2 of a second. LIGO works by splitting a laser beam down two perpendicular tunnels, each 4 kilometers long, roughly 2.5 miles, and measuring with extraordinary precision whether the length of those tunnels changes relative to each other. A gravitational wave passing through the detector compresses space in one direction and stretches it in the other, creating a difference in the two tunnel lengths that the instrument can measure. How small is that difference? The signal LIGO detected on that September morning represented a change in the length of a 4-kilometer tunnel of approximately 1,000th the diameter of a proton. A proton is already vanishingly small, millions of times smaller than the period at the end of a sentence, and the signal LIGO measured was 1,000th of that. Scientists spent years building instruments sensitive enough to detect a distortion that makes a single atomic nucleus look enormous by comparison. The signal came from two black holes, one approximately 36 times the mass of our Sun, the other approximately 29 times, that had spent over 1 billion years spiraling toward each other, accelerating in their final moments to a fraction of the speed of light and merging in a catastrophic collision approximately 1.3 billion light-years from Earth. That means the light reaching us from a galaxy at that distance today left when the most complex life on Earth was still single-celled organisms. The gravitational wave that arrived that morning had been traveling for 1.3 billion years before it passed through the bodies of the scientists who detected it, compressed and stretched the tunnels they built, and appeared in their data. The detection was announced in February 2016. A century after Einstein predicted them, humanity heard spacetime speak for the first time. But what LIGO heard was a single event, a brief, sharp signal from one specific catastrophic merger. What Nanograv heard was something categorically different. In June 2023, the North American Nanohertz Observatory for Gravitational Waves released the results of 15 years of accumulated data, and simultaneously, 3 other global collaborations released their own independent analyses of the same phenomenon: the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array. 4 teams, 4 datasets. One result: a gravitational wave background, a stochastic background, meaning a signal coming from so many overlapping sources simultaneously that it cannot be separated into individual events, was humming through all of space-time, not a single wave from a single merger, a continuous, omnidirectional resonance, like the combined vibration of millions of instruments playing simultaneously in every direction at once, at a frequency so low that a single wave takes years to complete one full cycle. The frequency of this background sits at approximately 32 nanohertz. To feel what that number means, the lowest audible sound a human ear can detect cycles roughly 20 times per second. This gravitational background cycles roughly 32 times per billion seconds. If you could somehow hear it, a single note would take more than a year to rise and fall. Not a tone, a geological patience. The 4 collaborations confirm the background through something called the Hellings-Downs correlation. This is the key. When a gravitational wave passes through 2 pulsars, those extraordinarily precise rotating stellar clocks scattered across our galaxy, it changes the timing of their pulses in a specific, mathematically predictable way that depends on the angle between them as seen from Earth. The relationship between the angle separating 2 pulsars and the correlation of their timing deviations produces a precise curve, derived mathematically by Ronald Hellings and George Downes in 1983, that is the unique fingerprint of gravitational waves and nothing else. Nanograv found that fingerprint. All 4 collaborations found it. This was not a detection of a possible signal. This was a confirmation. Something is vibrating spacetime on timescales of years across the entire observable universe, simultaneously. Right now, here is where the question becomes genuinely open. The leading explanation for the nanograv background points to supermassive black hole binaries, pairs of black holes containing hundreds of millions or even billions of solar masses, orbiting each other at the centers of ancient merging galaxies, distributed throughout cosmic history across billions of light years. Enormous populations of them, their gravitational wave output combining across cosmic time into a steady, omnidirectional roar. Most researchers consider this the most probable source, and the data is broadly consistent with it. But consistent with is not the same as explained by. Some components of the observed signal, its exact frequency distribution, certain features of its spectral shape, remain in discussion. A subset of physicists working in early universe cosmology have noted that several theoretical processes from the very early universe would produce gravitational wave backgrounds with characteristics overlapping what nanograv measured. Cosmological phase transitions, moments in the first fractions of a second after the Big Bang, when the fundamental forces of nature separated from a unified state, releasing vast amounts of energy, would generate gravitational waves at frequencies that could contribute to the background we observe today. Primordial inflation, the extraordinary burst of exponential expansion that cosmologists believe occurred in the universe's first tiny fraction of a second, would generate a gravitational wave background carrying the direct imprint of physics at the highest energies that ever existed. And some theoretical frameworks go further still. Models of a big bounce, a universe that did not begin from nothing but contracted from a previous state and rebounded, predict gravitational wave signatures that would originate from before what we call the Big Bang entirely. A previous aeon, in certain cosmological models, would leave gravitational echoes that survive the transition between one cosmic era and the next. None of these alternatives has been confirmed. None has been ruled out. The data cannot yet isolate whether any component of the nanograv signal originates from the first fractions of a second after the Big Bang, let alone from before it. That distinction between supermassive black holes and something far older requires sensitivity and frequency resolution that current instruments do not yet possess. This is the paradox at the center of the signal. We have confirmed a real, omnidirectional gravitational wave background permeating all of space-time. We have multiple physically legitimate explanations for it, and we cannot yet determine which one or which combination is true. The most important measurement in the history of gravitational wave astronomy sits inside an unresolved scientific debate that has profound implications for the nature of time itself. Let's examine this more carefully, because the significance of what gravitational waves can carry is easy to understate. Every other signal we use to study the early universe, light, radio waves, X-rays, infrared, ultraviolet, hits the same wall, the CMB barrier, the moment at 380,000 years after the Big Bang when the plasma cleared and light was first set free. Before that moment, all electromagnetic signals are permanently erased. Every photon that existed in the opaque era was scattered and rescattered until all directional and source information was destroyed. The CMB is not a window into the plasma era. It is the scar left when the plasma era ended. Informative, yes, but only about its own surface. Gravitational waves carry no electromagnetic charge. They interact with matter through gravity alone, and gravity's interaction with the plasma that filled the early universe was negligibly weak compared to the electromagnetic scattering that made that plasma opaque. Gravitational waves generated in the very first fractions of a second after the Big Bang, during inflation, during phase transitions, during whatever violent processes shaped the universe before its first millisecond, would have passed through the plasma era the way a breath of wind passes through fog, unscattered, unabsorbed, unchanged. They would still be here, diluted by 13.5 billion years of cosmic expansion, stretched to lower frequencies by the same expansion that stretches light into redshift, overwhelmed possibly by the contribution of black hole mergers accumulated across cosmic history, but present, embedded somewhere in the signal that Nanograv has already confirmed. Picture two messages sent from the same ancient moment, one written in light, intercepted, scrambled, destroyed by the plasma it tried to cross, leaving only the faint thermal afterglow of its scattering as the CMB, the other written in gravitational waves, passing through that same plasma as if it were not there, carrying its original content intact across 13 billion years, arriving at our detectors still holding, in principle, the information it was given at the moment of its creation. We have the ability to read the second message. We built the instruments. We confirmed the signal exists. We simply do not yet have the resolution to separate what it is saying. Two observatories are coming. LISA, the Laser Interferometer Space Antenna, is ESA's planned space-based gravitational wave detector, currently scheduled for launch in the 2030s. Where LIGO uses 4-kilometer tunnels on the ground, LISA will use laser beams stretching between 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, roughly 1.55 million miles, from each other. That is more than 6 times the distance from the Earth to the Moon. At those scales, LISA will detect gravitational wave frequencies far lower than any ground-based instrument can reach, frequencies that would carry the imprint of the early universe directly. The Einstein telescope, a proposed underground detector in Europe, will reach sensitivities LIGO cannot approach, opening the window on gravitational waves from sources and eras that current technology is simply blind to. These are not wishful thinking. These are funded, designed, peer-reviewed observatories in active development. And what they are hunting, what the physics says they have a genuine chance of finding, is the gravitational echo of the universe's first moment, or of whatever came before it. But to understand what that echo might actually be telling us, we need to confront the question that the language of gravitational waves is ultimately asking, not what happened in the first second of the universe, not what happened at 380,000 years, what happened at the beginning itself, at the moment that cosmology calls the singularity, the point where all of our equations break down and the universe, as far as our current physics is concerned, simply starts. Because here is the thing most people do not realize. That starting point, the Big Bang singularity, may not be a beginning at all. The singularity. That word sits at the center of every conversation about the origin of the universe, and almost everything most people believe about it is based on a misunderstanding. Not a small misunderstanding, a fundamental one. The kind that shapes how we think about time, about existence, about whether the question of what came before the Big Bang is even a legitimate scientific question, or simply a category error, like asking what is north of the North Pole. The standard picture most of us carry looks something like this. The universe began at a single point, impossibly small, impossibly hot, impossibly dense. Everything that exists, every galaxy, every atom, every photon that has ever traveled through space, compressed into a state of infinite density at a single moment called T0. Time zero, the beginning. And before that moment, by definition, nothing. Not empty space, not darkness, not waiting, nothing. That picture is not wrong exactly, but it is radically incomplete, and the incompleteness is not a matter of missing details. The incompleteness sits at the deepest level of the physics itself. Let's be precise about what a singularity actually is, because the word is doing enormous work here, and it is not doing the work most people assume. In 1965, the British mathematicians Roger Penrose and Stephen Hawking published what became known as the singularity theorems. working within the framework of Einstein's general relativity, the same theory that predicted gravitational waves, the same theory that describes the curvature of spacetime around massive objects. They proved mathematically that singularities are inevitable. Under the conditions that general relativity describes, if you trace the expansion of the universe backward in time, the equations inevitably converge on a point where density becomes infinite, volume becomes zero, and the geometry of spacetime ceases to be mathematically defined. This is an extraordinary result. But here is what it actually means, and what it does not. A singularity is not a physical object. A singularity is not a confirmed state of reality. A singularity is the point in a set of equations where the equations produce an answer of infinity, and infinity, in physics, is not an answer. Infinity is a signal, a red flag embedded in the mathematics itself, telling you that the theory you are using has reached the boundary of its own validity. Think of it this way. General relativity is one of the two great pillars of modern physics. The other is quantum mechanics, the theory that describes how matter and energy behave at the smallest imaginable scales. Both theories are extraordinarily well tested. Both produce predictions of astonishing precision in their respective domains. But they are also fundamentally incompatible with each other at the mathematical level. A complete theory of physics, one that works across all scales simultaneously, does not yet exist. Physicists call it a theory of quantum gravity, and it remains one of the deepest unsolved problems in all of science. General relativity governs the very large. Quantum mechanics governs the very small. And at the very beginning of the universe, when everything that exists was compressed into a space almost inconceivably tiny, both regimes apply simultaneously. The universe was both large in energy and small in scale, and that is exactly where general relativity breaks down. Physicists have a name for this unreachable era: the Planck epoch, named for Max Planck, the German physicist whose work in the early 20th century laid the foundations of quantum theory. The Planck epoch refers to the first 10 to the power of negative 43 seconds of the universe's existence. To understand how brief that is, the entire history of the observable universe, from the Big Bang to this moment, spans approximately 13.8 billion years, which works out to roughly 430 quadrillion seconds. The Planck epoch is the first sliver of time so short that if you divided 1 second into 10 million billion pieces, the Planck epoch would still be smaller than one of those pieces. No unit of human experience, no clock ever built, no measurement ever conceived approaches this timescale, and it is precisely at this scale that our best physics becomes genuinely silent, not uncertain, not approximate, silent. Every equation we have, every framework we trust, every result we can test and verify, all of it ceases to function in any reliable way before the Planck moment. The singularity that Penrose and Hawking proved is mathematically inevitable in general relativity sits inside this region, the region where general relativity itself has already broken down. It is a prediction of a theory, applied beyond the range where that theory is valid. This is not a fringe position. This is the mainstream scientific consensus. The singularity at T0 is not a confirmed physical reality. It is the point where our current description of reality runs out of language, and if it is not a beginning, if the equations that produced it are simply telling us they cannot describe what was there, then the question immediately and urgently becomes, what does a more complete theory of physics say happened at that moment? Alan Guth, a physicist then working at Stanford, published a paper in 1980 that transformed cosmology. His proposal, cosmic inflation, addressed something deeply puzzling about the universe we observe. The CMB, the oldest light in existence, looks almost identical in every direction, not similar, nearly identical with temperature variations of only 1 part in 100,000. This uniformity is extraordinary, and in the standard Big Bang model, without any additional mechanism, it is deeply mysterious. because regions of the sky on opposite sides of the CMB horizon were never in contact with each other. They were too far apart, expanding too fast, for any signal travelling at the speed of light to have carried heat between them and equalised their temperatures in the time available. Guth's solution was startling. He proposed that in the first tiny fraction of a second after whatever happened at T0, the universe underwent a period of exponential expansion, inflation, expanding by a factor of at least 10 to the power of 26 in an almost incomprehensibly short time. 10 to the power of 26 is a number so large it dwarfs the number of atoms in your body by a margin that language struggles to capture. This expansion was so rapid, so vast, that any initial region of the universe, no matter how small, was blown up to cosmic scales before the structures we observe today had time to form. Whatever small region happened to be smoothly uniform before inflation was stretched into the entire observable universe, explaining the CMB's extraordinary uniformity in a single elegant mechanism. Inflation also explains the large-scale geometry of space, why the universe appears flat rather than curved, and it explains the seeds of all structure, all galaxies, all clusters. Quantum fluctuations in the inflationary field, stretched to macroscopic scales, became the density variations that gravity later amplified into everything we observe. Guth's inflation was a profound achievement, but it carried an implication that opened a new and stranger question. In the mathematics of inflation, the inflationary field, the quantum field driving the exponential expansion, does not stop inflating everywhere simultaneously. Quantum fluctuations within the field cause different regions to stop inflating at different moments. Where inflation ends locally, a universe like ours is born, a hot, expanding Big Bang emerging from that local stopping point. But in the vast quantum field surrounding it, inflation continues. Other regions stop inflating. Other universes nucleate, endlessly. This is eternal inflation, a framework in which our Big Bang is not a unique event, but one bubble of ended inflation in an infinitely larger, perpetually inflating quantum landscape. In eternal inflation, our universe has no singular origin. It has a local birth, but that birth is embedded in something that had no beginning and may have no end. That idea is controversial. Measuring what lies beyond our own bubble is, by definition, beyond any instrument we can build. But it is not speculation. It is a mathematically rigorous consequence of inflationary theory, developed by Guth, Alexander Vilenkin, Andrei Linde, and others, published in peer-reviewed journals, and taken seriously by a significant portion of the cosmological community. Here is where the birth problem reaches its sharpest edge. The standard model places a singularity at the beginning. The singularity is where general relativity breaks down. General relativity breaks down because it does not include quantum mechanics. But the era where quantum mechanics must be included is precisely the era the singularity sits inside, which means the conclusion, the singularity, the true beginning, the hard edge of time, is a consequence of using a theory past its own limit of validity. We have proven, using mathematics, that a beginning must exist, and we have proven, using different mathematics, that the theory which produced that proof cannot be trusted at the moment that beginning occurs. The singularity may be telling us nothing about the universe. It may be telling us only about the limits of our own equations. This is where loop quantum cosmology enters the story, and it is worth being precise about what this framework is, because it is not speculation and it is not a fringe idea. Loop quantum cosmology, or LQC, was developed principally by Abhay Ashtekar at Pennsylvania State University and his collaborators over several decades of rigorous mathematical work. It has been published in peer-reviewed physics journals. It has been cited thousands of times. It represents one of the most mathematically developed attempts to apply quantum mechanics to space-time geometry itself, to do to gravity what quantum mechanics did to electromagnetism and the nuclear forces. In LQC, Space is not a smooth, continuous fabric that can be compressed to any size without limit. Space, at the Planck scale, is quantized, meaning it comes in discrete minimum units, the way energy in quantum mechanics comes in discrete packets called quanta. There is a smallest possible volume of space, just as there is a smallest possible energy for a given type of radiation. You cannot compress space below this minimum unit any more than you can have half a photon. The consequence of this single change, applying quantum mechanics to geometry itself, is profound. In general relativity, as you trace the universe backward in time and it contracts to smaller and smaller volumes, the density rises toward infinity. The singularity is the mathematical endpoint of that compression. But in LQC, as the universe contracts and density rises, quantum effects become dominant before infinite density is ever reached. The quantized nature of space generates a repulsive force, a quantum pressure, that resists further compression. The density reaches an enormous but finite maximum value, and then the collapse reverses. Contracts, halts, bounces. The Big Bang, in loop quantum cosmology, is not the beginning of everything. The Big Bang is a quantum rebound, what physicists call the Big Bounce, the moment when a previous contraction reversed into our current expansion. What we experience as the origin of our universe is, in this framework, the turnaround point of a cycle. Something was there before it. In 2025, researchers publishing in the journal EPL, Europhysics Letters, used LQC dynamics to show that the universe homogenizes, smooths out, rapidly after the bounce, producing conditions consistent with what we observe in our own cosmos. Let that land for a moment. This is not philosophy. This is peer-reviewed mathematics producing testable predictions about the state of the universe on the other side of what we call the beginning. LQC does not require a previous universe to have contained stars or galaxies or any structure we would recognize. It does not require life. It requires only that the contracting phase that preceded our bounce was real, that the universe we inhabit is not the first state of existence, but a continuation of something older that passed through its own ending and emerged as our beginning. Whether that is true, we cannot yet confirm. The signatures LQC predicts in the CMB and in the gravitational wave background are being actively investigated. The data exists. The instruments are looking. The mathematics has produced a specific, testable claim about reality, and that transforms the question of what came before the Big Bang from metaphysics into physics. Two frameworks, eternal inflation and loop quantum cosmology. Neither is mainstream consensus, neither is fringe. Both are legitimate, mathematically developed, peer-reviewed scientific proposals for what lies beyond the visible boundary of our universe. Both say the same thing. Through different mathematics and different mechanisms, our Big Bang was not a beginning. In one picture, it is a bubble born from a quantum field that has always been inflating, and always will be. One local event in an infinite, eternal landscape that has no first moment. In the other, it is a rebound, the universe collapsing into its smallest possible quantum state and erupting outward again, with the gravitational wave background potentially carrying the echo of the contraction that preceded it. And here is what makes this more than an abstract philosophical debate. If either of these frameworks is even partially correct, if our universe did emerge from something that preceded it, then the gravitational wave background confirmed by nanograv is not merely a record of black hole mergers throughout cosmic history. It is a medium, a channel, one that, given enough sensitivity, could carry in its structure the actual signature of what happened before the bounce, before the bubble, before the moment our equations currently call the beginning. But both LQC and eternal inflation are frameworks that operate in the mathematical space before our physics breaks down. To understand what might genuinely have existed on the other side, not as an equation, but as a universe, with its own history and its own end, we need to look at a third idea. One proposed not by a quantum gravity theorist, but by one of the most celebrated mathematical physicists of the 20th century. An idea that does not require quantum mechanics at all. An idea that suggests the universe does not bounce, it completes, and then it begins again. Roger Penrose is not a fringe thinker. He shared the Nobel Prize in Physics in 2020 for his work proving that black holes are a direct and necessary consequence of general relativity. He co-authored the singularity theorems with Stephen Hawking. He is one of the most mathematically gifted physicists of the 20th century, and his work spans geometry, cosmology, and the foundations of consciousness. When Penrose puts forward a scientific framework, the physics community does not dismiss it. It argues with it carefully, tests it rigorously, and takes the results seriously. His proposal for what came before the Big Bang does not invoke quantum mechanics. It does not require a bounce, a contraction, or a quantum pressure halting the collapse of space. His proposal says something stranger, and in certain ways more unsettling than either of those. It says the universe does not begin, it does not end, it completes. And then, seamlessly, without interruption, it begins again, infinitely, in cycles without a first or a final. But before we follow Penrose into that idea, we need to understand what loop quantum cosmology actually predicts about the universe on the other side of the bounce. Because the bounce is not just a mathematical convenience. The mathematics makes a specific, physical claim about what was there. In loop quantum cosmology, the moment of reversal occurs when the energy density of the collapsing universe reaches an almost incomprehensibly large but finite value, roughly 10 to the power of 96 kilograms per cubic meter. To feel the weight of that number, consider that water, ordinary water filling a glass, has a density of 1,000 kilograms per cubic meter. Nuclear matter, the densest substance that actually exists in nature, packed into the cores of neutron stars, reaches densities of around 10 to the power of 17 kilograms per cubic meter. The LQC bounce density is roughly 10 billion times denser than that, not infinite. But so far beyond any physical state we have ever observed that the difference between it and a neutron star is larger than the difference between a neutron star and empty space. At that density, the quantum nature of space-time geometry, the fact that space comes in discrete minimum units rather than being infinitely divisible, generates a repulsive pressure that overcomes gravitational collapse. The contracting universe does not reach a singularity. The equations do not break down. The density reaches its maximum, the quantum pressure pushes back, and what was collapsing becomes expanding. The bounce is not a metaphor. In the mathematics of LQC, it is a calculable transition with specific predicted properties on both sides. And in 2025, a paper published in EPL, Europhysics Letters, examined what those properties look like. The research found that LQC dynamics predict the universe homogenizes rapidly after the bounce, meaning it smooths out, loses the imprint of any irregular structure from the preceding contraction, and arrives at a state broadly consistent with the conditions we observe in our own early universe. The uniformity, the near flatness, the smooth distribution of energy that the CMB reveals, all of these, in LQC, are not mysteries requiring an additional explanation. They emerge naturally from the dynamics of the bounce itself. That is a significant result, not a proof, but a mathematically consistent, testable prediction that connects the proposed mechanism of a pre-Big Bang universe to the actual observations sitting in our data. The physics of the bounce raises a question that LQC itself leaves deliberately open, because the mathematics alone cannot answer it. What was the contracting universe actually like? LQC makes no requirement about this. The contracting phase that preceded our bounce could have been structured or featureless, dense with galaxies or empty of them, old or young. The framework that produces the bounce does not demand any specific history for the universe that came before. It demands only that a contracting phase existed, that it reached the quantum density threshold, and that the bounce produced the expanding universe we inhabit. Whether that previous universe contained stars or planets or chemistry or anything resembling the complexity we observe in our own cosmos, the equations do not say, and scientists are honest about that gap. The honest answer is, we do not know. We may never know with certainty. The bounce, in most LQC models, erases or scrambles the detailed structure of what preceded it, in much the same way the inflationary expansion of our universe erased the fine-grained structure of whatever seeded it. But the framework does not rule it out either, and that asymmetry, knowing that something was there but not knowing what, is one of the most genuinely strange positions science has ever occupied. It sits differently from ordinary scientific uncertainty. Normally, uncertainty means we need better data, more sensitive instruments, a longer baseline of observation. Here, the uncertainty is structural. The very mechanism that produced our universe may have destroyed the evidence of what came before it. We are, in a real sense, looking for the light of a candle that may have been extinguished before our eyes existed to see. Roger Penrose's conformal cyclic cosmology, CCC, approaches the question from an entirely different direction. Not from quantum mechanics, not from the compression of space into discrete units, from geometry, from the deep mathematical structure of spacetime itself, and from a profound observation about what happens at the two extreme ends of a universe's life. Let's think about what the very far future of our universe looks like. Roughly 5 billion years from now, our sun will exhaust its hydrogen fuel and expand into a red giant, eventually shedding its outer layers. Over hundreds of billions of years, the stars of the Milky Way will burn out one by one. The universe will grow colder and darker, over timescales so vast they make the current age of the cosmos look like a single heartbeat. Matter will gradually fall into black holes at the centers of galaxies. Those black holes will consume their surroundings over periods measured in tens of trillions of years. And then, in the extraordinarily distant future, over timescales measured in numbers with more than 60 zeros, even those supermassive black holes will evaporate. This process is called Hawking radiation, named for Stephen Hawking, who predicted it in 1974. At the quantum level, pairs of particles are constantly being created and annihilated at the boundary of a black hole, called the event horizon. Occasionally, one particle falls in while the other escapes. Over immense time, this bleeds energy away from the black hole. The black hole slowly, imperceptibly loses mass, and eventually it radiates away entirely, leaving behind only a thin wash of thermal radiation spreading through empty space. The end state Penrose envisions is a universe containing essentially nothing except that radiation. No matter, no structure, no black holes, just a vast, expanding, geometrically smooth field of low-energy photons spreading through an ever-growing void. Here is the crucial insight at the center of CCC. In a universe containing only massless radiation, only photons, the concept of distance loses its meaning. Photons have no rest mass. For a massless particle traveling at the speed of light, time does not pass. Scale has no reference point. A universe filled only with massless radiation, Penrose argues, is geometrically identical, in a precise mathematical sense called conformal equivalence, to the beginning of an expanding universe. The vast, cold, smooth end of one cosmic aeon maps, through a mathematical transformation that preserves angles and shapes but not scales, directly onto the hot, dense, smooth beginning of the next. The end of one universe seeds the beginning of another, not through a bounce, not through a quantum pressure, through a geometric transformation in which the enormous and the infinitesimal become, in the appropriate mathematical framework, indistinguishable. And if that mapping is real, if the death of each aeon genuinely carries information into the birth of the next, then that information should leave a mark, a specific, detectable mark. Penrose called those marks Hawking points. The reasoning goes like this. As the supermassive black holes of the previous aeon evaporate over those incomprehensibly long time scales, the final burst of Hawking radiation they release concentrates into a point, a hot spot in the radiation field that fills the dying universe. That concentration, when it maps through the conformal transformation into the birth of the next aeon, should appear as a subtle circular temperature anomaly in our own CMB, a faint ring of slightly elevated temperature, the ghost of a black hole from the universe before ours, pressed into the oldest light of our own. Penrose, working with the Armenian astrophysicist Vahe Gurzadyan, claimed in a series of papers beginning around 2010 to have found exactly these signatures in the WMAP satellite data, and later in the Planck data. Circular temperature patterns in the CMB, they argued, consistent with what Hawking points would produce. The response from the broader scientific community was extensive, careful, and ultimately sobering. Multiple independent research teams reanalyzed the same CMB datasets. Their conclusion? The circular patterns Penrose and Gurzadyan identified were not statistically distinguishable from what ordinary random fluctuations in the CMB would produce. The signal was not anomalous. The patterns did not exceed what the standard model of cosmology, with no reference to previous aeons, would predict by chance. And in 2024, a research team applied machine learning algorithms to scan across 50 million sky positions in the Planck CMB data, the most exhaustive automated search for Hawking point signatures ever conducted. The algorithms found no statistically significant confirmation. This is not a dismissal of CCC as a framework. Penrose's mathematics remain published, peer-reviewed, and scientifically coherent. CCC is a legitimate scientific theory, but as of the best available evidence, the specific observational prediction it makes, Hawking points in the CMB, has not held up under rigorous independent testing. Science does not require a theory to be immediately confirmed, but it does require that predictions be testable and that negative results be taken seriously. CCC currently sits in an unusual position, mathematically compelling, observationally unconfirmed, and still very much alive as a framework worth continued investigation. The big bounce of loop quantum cosmology and the cyclic aeons of conformal cyclic cosmology share a premise so fundamental it is worth stating plainly. Both say the same thing about the Big Bang. Both say it was not a beginning. They arrive at that conclusion through entirely different mathematics, using entirely different physical mechanisms, making entirely different predictions about what evidence a previous universe would leave behind. LQC produces a bounce through quantum repulsion at extreme density. CCC produces a cycle through geometric equivalence at extreme emptiness. They do not agree on the mechanism. They do not agree on the physics. They do not share a mathematical framework at any level, but both conclude that our universe emerged from something, that the moment we call the beginning is a transition point, not an origin, that whatever existed before the Big Bang left an imprint, encoded either in the gravitational wave background that nanograv has confirmed, or in the CMB itself, or in both, and that imprint, if we build the right instruments and ask the right questions, is recoverable. That is a remarkable convergence for two frameworks that otherwise have almost nothing in common, and it creates a pressure on the data that is difficult to ignore, not because either theory has been confirmed, but because both, independently, predict that the CMB and the gravitational wave background should carry information from before our universe's birth, and both are being actively tested against the most sensitive datasets ever compiled. The question is no longer whether a pre-Big Bang universe is theoretically possible. Multiple rigorous peer-reviewed frameworks say it is. The question has shifted to something sharper and something that observational science can actually engage with. Does the data we already have say anything about it? And here is what makes the next part of this story genuinely different from everything we have covered so far. We have spent considerable time with frameworks, with the mathematics of what might have preceded our universe, with the theoretical predictions of what signals it might have left, with the confirmed existence of a gravitational wave background that travels freely through barriers that stop all light. But the CMB itself, the oldest electromagnetic signal we will ever possess, already carries within it 4 persistent, unexplained anomalies that no standard model can account for. Anomalies that were measured not once but twice by 2 independent satellite missions built a decade apart. Anomalies that survived every attempt to explain them away. Some researchers believe those anomalies are not noise, not statistical flukes, not imperfections in our instruments. They believe those anomalies are fingerprints, left not by processes that occurred after the Big Bang, but by whatever happened before it, and the case those researchers are making is more disturbing and more precise than most people realize. The oldest image in existence has 4 things wrong with it. Not slightly wrong, not within the noise, wrong in ways that have survived every attempt to explain them, every reanalysis, every upgraded dataset, every independent instrument pointed at the same ancient light. Wrong in ways that 2 separate satellite missions, built years apart, using different technologies, operated by different teams, have both confirmed, independently, in their own data. 4 anomalies. 4 patterns embedded in the very fabric of the oldest observable light in the universe. And after decades of careful, serious scientific scrutiny, not one of them has a consensus explanation. This is not a fringe claim. This is the current state of the data. To understand why these 4 anomalies are so troubling, we first need to understand what the CMB is supposed to look like, what our best model of cosmology confidently predicts we should find when we map the oldest light in the universe to its finest detail. The standard model of cosmology, the one that has survived decades of observational tests, predicts that the CMB should be statistically isotropic. Isotropic is a technical term, but its meaning is straightforward. The same in all directions. The universe, on the very largest scales, should look statistically identical, regardless of which way you point your telescope. No preferred direction, no preferred hemisphere, no alignment with any particular structure. Certainly not with the plane of our own tiny solar system, which is a vanishingly insignificant speck in the context of the entire observable cosmos. The CMB temperature variations that do exist, those 1 part in 100,000 fluctuations that Planck measured with extraordinary precision, should be distributed randomly, like static on an old television screen, following a well-understood statistical pattern that the standard model predicts with great confidence. Random, but with a specific statistical texture. Uniform in the sense that no direction is special, no region dominates, no pattern repeats. That is what the model predicts. And for the most part, at small and medium angular scales, the CMB matches those predictions beautifully. The agreement between theory and observation at those scales is one of the greatest achievements of modern cosmology. But at the very largest scales, across the widest angles in the sky, the broadest features of the CMB map, something is wrong. And it has been wrong in the same 4 specific ways since the first precise satellite measurements arrived. The ESA Planck satellite operated from 2009 to 2018, mapping the CMB across the entire sky with a sensitivity and resolution that no previous instrument had approached. Its predecessor, NASA's WMAP satellite, had already been mapping the CMB since 2001. These 2 missions, built by different agencies on different timelines, with different instruments and different systematic errors, converged on the same map of the oldest light in the universe. And in both maps, persistently, reproducibly, undeniably, the same 4 anomalies appear. The first is called the hemispherical power asymmetry. One half of the sky, when you divide it optimally, carries roughly 7% more CMB temperature variation than the other half. Not a tiny effect hidden deep in the noise. 7%, a systematic difference in the energy content of the CMB across the 2 hemispheres of the sky. WMAP first detected this asymmetry in 2004. Planck confirmed it independently with higher precision measurements. The Standard Model has no natural explanation for why one side of the sky should carry measurably more CMB power than the other. The universe, in the standard picture, has no preferred half, 7%, in the most fundamental large-scale structure of the oldest observable light, confirmed by 2 independent satellites. The second anomaly is the cold spot. In the southern hemisphere of the CMB sky, centered on a specific set of coordinates, lies a region approximately 10 degrees across. 10 degrees is enormous on the sky. For reference, the full moon spans about half a degree as seen from Earth, so this cold region stretches across the equivalent of roughly 20 full moons placed side by side. Within this region, the temperature of the CMB drops measurably below what surrounds it, and not just slightly. The depth and angular size of this cold region exceed what ordinary random fluctuation in the Standard Model can statistically produce. Multiple analyses have tested whether the cold spot could be a coincidence. The answer, consistently, is that it is unlikely enough to require an explanation, though no consensus explanation exists. Some researchers initially proposed that a supervoid, an enormous genuine underdensity in the distribution of galaxies lying between us and the CMB, might account for the cold temperature through a gravitational effect on the photons passing through it. Studies of the galaxy distribution in that region have found some evidence for an underdensity, but whether it is large enough and empty enough to fully account for the cold spot remains actively debated. The Standard Model fluctuation alone remains an insufficient explanation. The third anomaly has a name that reflects the frustration it caused when researchers first identified it: the axis of evil. That name, used in a peer-reviewed paper published in 2005, was not chosen for drama. It was chosen because of what the alignment actually implies. 2 large-scale features of the CMB, called the quadrupole and the octupole, represent the broadest, most sweeping temperature variations across the entire sky. In the Standard Model, these features should point in random directions, uncorrelated with anything in our local cosmic neighborhood. Instead, they align conspicuously, persistently with statistical significance that survived multiple independent analyses, with the plane of our own solar system, with the ecliptic, with the flat disk traced by Earth's orbit around the Sun. Think about what that means for a moment. The broadest features of the oldest light in the observable universe, light that has been traveling for 13.8 billion years, align with the plane of our tiny planetary system, a structure that formed less than 5 billion years ago in one unremarkable corner of one unremarkable galaxy, embedded in a cosmos of hundreds of billions of galaxies. The probability of this alignment occurring by chance in a truly isotropic CMB is small enough that researchers gave it that bleak name, and the alignment persists in the Planck data, measured independently from WMAP. No standard physical mechanism connects the largest features of the CMB to the geometry of our solar system. The distance scales involved make any causal connection essentially impossible within our current framework. The fourth anomaly is subtler, but in some ways the most statistically striking of all. At large angular scales, separations greater than 60 degrees across the sky, the CMB shows almost no temperature correlation. Temperature correlation means if you pick a point on the CMB map and measure its temperature, how well does that predict the temperature of a point 60 or 90 or 120 degrees away? In the Standard Model, the prediction is clear and specific. There should be measurable, calculable correlations at those large angles. The physics of the early universe, the way density fluctuations grew and travelled, produces a definite statistical signature at every angular scale. At large angles, that signature is essentially absent, missing, not reduced. The correlations the Standard Model confidently predicts simply are not there. Here is what makes these 4 anomalies collectively so difficult to dismiss. Each one, taken individually, sits at a statistical significance of between 0.1 and 1%. That means, for each anomaly in isolation, the probability of it occurring by random chance in a truly standard universe is somewhere between 1 in 100 and 1 in 1,000. Unusual, but not impossible. The problem is the combination. All 4 anomalies persist. All 4 appear in both WMAP and Planck data. All 4 have survived reanalysis, systematic error checks, foreground removal improvements, and instrument upgrades, and all 4 point, in different ways, toward the same region of the CMB sky. The large-scale structure, the broadest features, the oldest and deepest layer of the oldest light we can ever observe. The probability of all 4 persisting simultaneously in the same dataset, pointing in the same broad direction, if the standard model is complete and correct. That probability is not easily calculated, but it is considerably smaller than any one anomaly in isolation. Science does not have a clean consensus number for it, but the scientific literature is clear that their simultaneous persistence is harder to explain away than any individual anomaly, and that the standard model, as currently constructed, offers no natural account for any of them. And this is where the story reaches its most uncomfortable point. Some physicists, publishing in peer-reviewed journals working within established theoretical frameworks, have proposed that these anomalies are not anomalies at all. They are imprints, physical marks left in the CMB, not by processes that occurred after the Big Bang, but by conditions that existed before it, before the wall, before the plasma era, before the moment our universe became visible to any electromagnetic instrument. The hemispherical asymmetry could reflect a pre-inflationary inhomogeneity, a non-uniform energy distribution in whatever preceded inflation, stretched across our entire sky by the subsequent expansion. The missing large angle correlations could reflect a finite topology, the universe having a specific shape and size that cuts off correlations above certain scales, a shape inherited from the contracting phase that preceded the Big Bounce. The axis of evil's alignment with the ecliptic might reflect a genuinely preferred direction in the pre-inflationary vacuum state, a direction that the subsequent expansion did not fully erase. These are not confirmed interpretations. They are scientifically published hypotheses, grounded in legitimate theoretical frameworks. And what makes them difficult to simply dismiss is that they make a specific, testable claim. If these anomalies trace to pre-Big Bang physics, the gravitational wave background should carry correlated signatures. And future detectors sensitive enough to read those signatures will either confirm or refute the connection. Let's be honest about what we know and what we do not. We know the 4 anomalies are real. 2 independent satellite missions confirmed them. The scientific community accepts their existence. What remains debated, vigorously, seriously, with published papers on multiple sides, is what they mean. The most cautious interpretation is that they reflect unknown systematic errors in the data, or statistical flukes that happen to persist across 2 data sets, or some physical effect within our own cosmic neighborhood that imprints on the CMB. Some researchers hold this position. They are not wrong to be cautious. Science demands caution before extraordinary conclusions. The most ambitious interpretation, held by a smaller but serious and credentialed group of researchers, is that they are genuine imprints from before the Big Bang, that the universe did not begin in a state of perfect symmetry, and that whatever state it emerged from left marks in the geometry of spacetime that survived inflation, survived the plasma era, and are still visible in the oldest light we can observe. That the CMB is not just the oldest image of our universe, that it is, in certain of its features, the oldest image of something older still. Neither interpretation has won. The data exists. The anomalies exist. The debate is ongoing and active. But there is one thing both sides agree on. The standard model, as currently constructed, cannot explain all 4 anomalies simultaneously. Something is missing, whether that something is a mundane systematic effect, an undiscovered mechanism within our own universe, or a physical signature from a universe that preceded ours, that question is open. And it is open in a way that next-generation instruments are specifically being designed to address. 2 CMB experiments are in development that will push far beyond what Planck achieved. CMBS-4, a next-generation ground-based observatory funded by the US Department of Energy and the National Science Foundation, currently in design and planning, will deploy an array of telescopes in Chile and at the South Pole with sensitivity to CMB polarization patterns that Planck could only partially measure. LightBird, a JAXA space mission currently in development for launch in the late 2020s, will map the large-scale CMB polarization from space at resolutions that will either sharpen the anomalies into a clear signal or resolve them into ordinary noise. Both missions are deliberately designed to probe the physics of the very early universe. Both will generate data that the pre-inflationary and pre-Big Bounce hypotheses make specific, testable predictions about. And that is the honest state of where we are. Not at the end of this question, not even close. We have the oldest image ever captured. We have 4 things wrong with it that no one can satisfactorily explain. We have theoretical frameworks that connect those wrong things to physics older than our universe. And we have instruments under construction that may, within a decade, tell us whether those frameworks are pointing at something real. The fingerprints are in the data. What we do not yet know is whose they are. And understanding that, understanding the full weight of what that uncertainty means, and what it would mean for us if the answer turned out to be something that genuinely came before, requires stepping back from the anomalies themselves and asking the larger question that has been building beneath all of this from the very beginning. Science is now, for the first time in human history, asking whether a universe preceded ours, not as philosophy, not as metaphor, with real instruments, real mathematics, and a set of open questions that has a definitive shape. The question is no longer whether it can be asked. The question is whether we are ready for the answer. Science changes slowly, and then, occasionally, all at once. For most of human history, the question of what existed before the Big Bang belonged to philosophy, to theology, to the private hours of thinkers lying awake in the dark, not because scientists lacked curiosity about it, but because the question had no empirical traction. No measurement could reach it. No instrument could point at it. The question was real, but science had no tools to hold it. That has changed, and the change is recent enough that most people have not yet registered how profound it is. We are not at the point of confirmation. We are not at the point of proof, but we have crossed a threshold that is, in its own way, just as significant. The question of what came before our universe has moved, quietly, rigorously, without public fanfare, from the domain of speculation into the domain of active scientific investigation. And that transition carries consequences that science is only beginning to fully understand. Let's step back and look at the full picture of what we actually have. We have the James Webb Space Telescope's early galaxy findings, JWST Z14-0, confirmed spectroscopically at a redshift, placing it just 290 million years after the Big Bang, already spanning 1,600 light-years, already producing oxygen that required multiple generations of stellar life and death to create. We have MOM Z14, confirming that this was not an isolated anomaly but a pattern. We have a growing catalogue of early massive galaxies, the ones researchers informally called the red monsters, that appear far too large, far too chemically evolved, far too structured for a universe that young. Our best model of how galaxies form, tested across decades of observation, cannot comfortably accommodate them without significant revision to the physics of the very first moments of cosmic history. We have the nanograv gravitational wave background, confirmed, real, omnidirectional, detected simultaneously by 4 independent international collaborations across 3 continents after 15 years of data collection. A hum running through all of spacetime at a frequency so low that a single wave takes years to complete one cycle. Its most probable source involves supermassive black hole binaries, but that explanation remains incomplete, and several well-developed theoretical frameworks predict that a component of this background may trace to the first fractions of a second after the Big Bang, or to processes that preceded it entirely. We have 4 CMB anomalies, documented in data, surviving every reanalysis, confirmed independently by 2 satellite missions built a decade apart, a hemispherical power imbalance of 7% across the entire sky, a cold spot larger than 20 full moons that no standard model can statistically reproduce, an alignment between the broadest features of the ancient light and the geometry of our own solar system that has no conventional physical explanation, and a silence at large angular scales where the standard model confidently predicts correlation should be present, and it simply is not. None of these, in isolation, constitutes proof of anything beyond our current universe. Each one, taken alone, has proposed explanations that remain in active scientific debate. But the convergence, 3 independent streams of observation, using 3 completely different physical phenomena, pointing toward the same inadequacy in our current framework, creates a weight of evidence that cosmology is genuinely grappling with. Something is missing from our picture of how the universe began, and several serious, peer-reviewed scientific frameworks agree on what that something might be. Before we turn to the instruments, there is one more thread running through all of this that deserves to be pulled. In 1974, Stephen Hawking published a result that shocked theoretical physics. He demonstrated that black holes, which general relativity describes as regions of spacetime so severely curved that nothing, not even light, can escape, are not perfectly black. At the quantum level, a slow, continuous radiation seeps out from the region just outside a black hole's boundary. This radiation, now called Hawking radiation, carries energy away from the black hole. Over immense timescales, the black hole loses mass. It shrinks, and eventually, it evaporates entirely, leaving behind, according to the original calculation, nothing but thermal radiation. This produced a problem so severe that physicists have been arguing about it for 50 years. The problem is information. In quantum mechanics, the theory governing how matter behaves at the smallest scales, information is sacred. The detailed description of any physical system, its exact quantum state, can transform and spread and become encoded in different physical forms, but it cannot be destroyed. This is a fundamental law, as foundational to quantum mechanics as conservation of energy. Information, in the quantum mechanical sense, is indestructible. But Hawking's calculations suggested that when a black hole evaporates, the information about everything that fell into it, every particle, every quantum state, every piece of physical description of every object that ever crossed the event horizon, emerges only as featureless thermal radiation, random, patternless, the information gone, permanently destroyed. This created a direct, irresolvable conflict between general relativity and quantum mechanics, 2 of the most precisely verified theories in the history of physics, directly contradicting each other at the moment of black hole evaporation. Most physicists now believe, based on theoretical arguments developed over the past 2 decades, including work by Juan Maldacena at the Institute for Advanced Study in Princeton, that information is not actually destroyed, that it is encoded in some form we do not yet fully understand, in the radiation a black hole emits as it evaporates. The information survives, transformed and scrambled, but present. This matters profoundly to the question we are carrying. If information cannot be destroyed, even when matter collapses into a black hole and evaporates over trillions of years, if the quantum rules governing what survives a black hole's complete evaporation are strong enough to preserve information through that process, then what about information that existed in a universe before a big bounce? What about the physical content of an aeon that completed its full cycle, all its black holes evaporated, and its remaining radiation mapped conformally into the beginning of the next? What about the contracting phase that preceded our bounce? Some physicists argue that the same principles governing black hole information survival would apply to cosmic transitions, that the information describing a previous universe would not simply vanish at the bounce or at the transition between aeons, but would survive encoded in the state of the universe that emerged. If true, that information could be detectable, not as a direct image, not as anything we could reconstruct into the landscape of a previous cosmos, but as statistical correlations, anomalous patterns, or specific signatures in the gravitational wave background, or the CMB, exactly the kinds of signals we are already finding difficult to explain. This connection between the black hole information paradox and the question of a pre-Big Bang universe is not mainstream consensus, but it is a legitimate, actively published scientific discussion, and it adds a layer to the question that is genuinely important. If information survives cosmic transitions, then our universe is not just potentially the child of a previous one, it may be carrying that previous universe's fingerprints in its own physics. Right now, embedded in data we can read with the right instruments, here is the most uncomfortable version of where we stand. We have data that we cannot explain. 4 anomalies in the oldest observable light, a gravitational wave background whose full origin remains open, early galaxies that our best model of structure formation cannot comfortably accommodate, and we have multiple rigorous, peer-reviewed theoretical frameworks that predict exactly these kinds of unexplained features, but only if our universe was preceded by something else. The frameworks are not confirmed, the data is not conclusive, but the alignment between what the theories predict and what the data shows is precise enough that dismissing it requires an alternative explanation. And no alternative explanation, no conventional mechanism operating entirely within the standard model, has yet provided a complete account of all 4 CMB anomalies, the early galaxy problem, and the gravitational wave background simultaneously. Science does not prove things by elimination. Absence of an alternative is not confirmation of a hypothesis, but it does mean that the hypothesis of a pre-Big Bang universe, born from a bounce or inherited from a previous aeon, or seeded by an eternal inflationary field, is not standing in contradiction to the data. It is standing in alignment with the data in ways that matter, and no current instrument can resolve this. That is the honest position. No telescope alive today, no detector currently operational, has the sensitivity or the frequency range to definitively confirm or deny whether any component of the gravitational wave background originates from before our universe began. No CMB satellite currently in operation can resolve the large-angle anomalies into a clear causal signature. No galaxy survey has mapped enough of the early universe to fully characterize how dramatically the standard model needs to be revised. The question is real. The evidence is suggestive. The answer is not yet within reach. But it will be. LISA, the Laser Interferometer Space Antenna, is ESA's planned space-based gravitational wave observatory. 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers, roughly 1.5 million miles, will form a gravitational wave detector of unprecedented scale. At those baseline distances, LISA will be sensitive to gravitational wave frequencies far lower than anything LIGO or any ground-based detector can reach. Frequencies that correspond to processes in the very early universe, phase transitions, inflationary dynamics, or the gravitational signature of a contracting phase that preceded our Big Bang. LISA is currently planned for launch in the 2030s, with the observatory operating for at least 4 years of primary science. The Einstein telescope is a proposed next-generation ground-based gravitational wave observatory designed to be built underground in Europe to shield it from the seismic noise that limits surface detectors. Its planned sensitivity is roughly 10 times greater than advanced LIGO across a wider frequency band. At that sensitivity, it will open a window on sources near us entirely invisible to current instruments, including potentially the primordial gravitational wave background generated in the first fractions of a second of the universe's history. CMBS-4, a next-generation ground-based CMB observatory funded by the US Department of Energy and National Science Foundation, currently in development for deployment in Chile and at the South Pole, will measure CMB polarization patterns with a sensitivity that Planck could not approach. Polarization, the way the CMB's light waves are oriented as they travel, carries different information from temperature alone, and some of the most powerful signatures of primordial gravitational waves and pre-inflationary physics are predicted to appear there first. LIGHTBIRD, a JAXA space mission currently in development, will map the large-scale CMB polarization from space with a precision specifically designed to detect or definitively constrain the signature of primordial gravitational waves from inflation and from whatever may have preceded it. These 4 instruments share something significant. Each of them was designed explicitly to probe physics at the absolute earliest accessible moments of cosmic history. Each of them makes specific predictions testable only if we can push our measurements closer to, or through, the barriers that current instruments cannot cross. And each of them is sensitive, in different ways, to exactly the kind of signals that a pre-Big Bang universe would leave behind. They are not being built to answer this question. They are being built to answer their own primary science goals, which are already extraordinary. But the question of what came before our universe is now squarely within the reach of the measurements they will make. Let's think about what it would mean, genuinely, concretely, for one of these instruments to find something. Not proof of a previous universe. Science rarely delivers proof in a single measurement. What LISA finding a gravitational wave component inconsistent with all known post-Big Bang sources would deliver is a constraint, a narrowing of the space of possible explanations that pushes the pre-Big Bang hypothesis from suggestive to seriously supported. What's CMBS-4 mapping a large-angle anomaly that grows sharper with higher sensitivity rather than dissolving into noise would deliver is the same. Evidence that the pattern is real, physical, and demands a physical explanation. Equally important is the possibility of non-detection. If LISA maps the gravitational wave background across its full frequency range and finds it entirely consistent with supermassive black hole binaries and nothing more, if the primordial component is absent or too small to detect, that is also a result. That constrains the pre-Big Bang models. It tells us that whatever preceded our universe, if anything did, left a gravitational wave signature too faint for our instruments to read, which narrows the space of possible previous universes significantly. Science advances through both confirmations and constraints. The 2030s will almost certainly deliver major new constraints on whether the signals we currently cannot explain trace to physics before the Big Bang. Whether those constraints point towards something or rule things out, either result will transform our understanding. That is what makes this decade genuinely historic in ways that even most working scientists have not fully absorbed. Instruments are being built right now, funded, designed, tested, that will return data on the deepest question physics has ever formulated, not as a philosophical exercise, as a measurement program with defined targets and defined expectations. Webb cracked something open that cannot be closed. When JD's GSZ 14.0 appeared in the data, when the spectroscopic confirmation returned a redshift of 14.32 and the reality of a chemically mature galaxy existing at 290 million years old became undeniable, the scientific community did not simply update a parameter and move on. It was confronted with a signal that the standard model, as constructed, could not naturally produce. And in confronting that, it was forced to look more carefully at all the other signals it had been quietly noting for years. the gravitational wave background, the CMB anomalies, the theoretical frameworks that had been developing rigorously in the peer-reviewed literature without quite reaching critical mass. Webb did not discover that our universe had a predecessor. Webb made it impossible to avoid asking whether it did, and now the asking has a specific, defined shape. Real instruments, real frequencies, real angular scales, real polarization signatures, real timelines. The 2030s will not deliver a definitive answer to everything. Science never works that way. But the 2030s will deliver measurements that no generation before ours could make, about questions no generation before ours had the tools to ask with this precision. The signal that started all of this came from a galaxy 290 million years old, carrying oxygen that should not have been there. Data that was wrong in a way that mattered. Data that would not resolve into anything ordinary, no matter how carefully you check the instruments or reran the analysis. Something in the universe, something in its very first moments, or in whatever came before them, left that data wrong in exactly the same direction that multiple independent lines of evidence keep pointing. And what that means, what it would mean for us, for time, for the nature of existence itself, if the signal we are hearing truly originates from before the beginning, is what we have been moving toward since the very first image Webb sent back. The answer, if it comes, will not arrive as a headline. It will arrive as a number, a correlation, a frequency component that cannot be accounted for by anything born inside our universe. And in that quiet, precise mathematical moment, everything we think we know about beginnings will need to be held differently. That number will arrive quietly, not as an announcement, not as a press conference moment broadcast across the world, as a number in a data set, sitting in a table of values on a screen in a room where a small group of scientists will have been expecting it, or something very much like it, for years. A frequency, a correlation coefficient, a spectral index that does not match any known post-Big Bang source, and someone in that room will go still and recheck the calibration, and recheck the foreground subtraction, and then pull up the theoretical prediction they have had printed and filed for the better part of a decade, and the number will still be there. Science rarely announces its most profound moments loudly. The discovery that the universe was expanding, one of the most transformative revelations in the history of human knowledge, arrived in the comparison of faint smudges on glass photographic plates. The confirmation of gravitational waves arrived as a chirp lasting a fraction of a second in data that most of the world slept through. The deepest truths about reality have a habit of arriving in forms so quiet that only the people who have spent years preparing to recognize them understand, in the first moment, what they are looking at. We are not at that moment yet, but we are closer to it than any generation before us has ever been. Our universe is 13.8 billion years old. That number is precise, derived from multiple independent measurements, and represents one of the great achievements of modern observational cosmology. In human terms, if you compressed the entire history of the cosmos into a single calendar year, the Earth would not form until early September. Human civilization would not appear until the final 11 seconds of the final day of December. The span of a single human life would occupy less than a quarter of a second, and all of that, the full sweep of cosmic history, every galaxy, every star, every atom that has ever existed inside our observable universe, may represent one episode in a story so much longer that no unit of human time can meaningfully contain it. That possibility is not science fiction. It is the implication of peer-reviewed theoretical frameworks developed by serious physicists at major institutions across several decades of careful mathematical work. Loop quantum cosmology says the universe was born from a contracting phase that preceded our Big Bang, a bounce from something that came before. Conformal cyclic cosmology says our universe is one aeon in an infinite sequence, each seeded by the dying radiation of its predecessor. Eternal inflation says our Big Bang was one bubble in a quantum field that has been inflating forever and will continue to do so without end. All three are different, all three are legitimate, none is confirmed, and all three share the same foundational conclusion. The moment we call the beginning was a transition, not an origin. The CMB wall is real. The electromagnetic horizon is permanent. No telescope using light will ever see through it, but gravitational waves cross it freely, traveling through the geometry of space-time itself, indifferent to plasma, indifferent to barriers, carrying in their oscillation patterns whatever information was encoded in them at the moment they were generated. A nanograph has confirmed that a background of these waves, omnidirectional and persistent, hums through all of space-time right now. Its full origin remains scientifically open, and the instruments being built to characterize it more precisely are among the most technically ambitious scientific projects in human history. The CMB itself, the oldest image we will ever possess, carries 4 anomalies that no standard model can explain, confirmed by 2 independent missions, surviving every reanalysis, statistically significant individually, harder to dismiss collectively, and connected in several peer-reviewed theoretical proposals to physics that predates our universe's visible boundary. And Webb's early galaxies, JD's GSZ140, MOM-Z14, the red monsters, sit in a part of cosmic history where our best model of structure formation struggles to accommodate them, demanding revisions to the physics of the very first moments of the universe that may, when those revisions are made, change what we believe about what came before those moments. This is the full picture, not a single dramatic discovery. A convergence. 3 separate branches of observational science, using completely different instruments, measuring completely different physical phenomena, all pointing toward the same inadequacy in our current understanding of how the universe began. Science has no confirmed signal from before the Big Bang. That sentence needs to be said plainly, and it needs to be held alongside everything else we have covered. The anomalies are real, but unexplained. The gravitational wave background is real, but its origins are not fully resolved. The early galaxies are real, but the model revisions they demand are still being worked out. Loop quantum cosmology is mathematically rigorous but observationally unconfirmed at the level of the bounce. Conformal cyclic cosmology is intellectually compelling, but its specific CMB prediction, Hawking points, has not survived independent testing with the precision needed. The honest position is exactly this. Science has legitimate reasons to keep listening, not proven reasons, not confirmed reasons, legitimate ones. Reasons grounded in real data, real mathematics, and real peer-reviewed frameworks that make real, testable predictions. And that distinction matters enormously, because there is a profound difference between a question that is open because no one has thought carefully about it, and a question that is open because the best minds in the relevant fields have thought extremely carefully about it and arrived at a position of structured, productive uncertainty. We are in the second case. The question of what came before our universe is open not because it is vague or unanswerable in principle. It is open because the instruments precise enough to constrain it meaningfully have not yet been built. LISA is not yet in space. CMBS4 is not yet taking data. Lightbird is not yet mapping the large-scale polarization of the ancient light. The Einstein telescope is not yet operational. The measurements that will genuinely narrow the possibilities or confirm one of them are years away from being made. And in that gap between what we currently have and what we are about to have, we occupy a strange and remarkable position. We are the generation that asks the question with enough precision to know what the answer would require. We may or may not be the generation that receives it. Here is something worth sitting with. Every galaxy Webb found that challenged the standard model, every oxygen signature in a universe too young to contain oxygen, every structure too large and too formed to have assembled in the time available, forced a question. And that question, in every case, was not simply, how do we fix the model? The deeper question underneath the data was always, what does this tell us about the moment before this? What does the existence of something that should not yet be here tell us about the conditions that produced it? Webb does not see before the Big Bang. Webb sees after it, in extraordinary detail, closer to the beginning than any instrument before it. But in doing so, it keeps revealing that the beginning itself is not where we thought it was. Not as simple as we thought. Not as clean. The models that describe the first moments of the universe were built without Webb's data, and Webb's data is not cooperating with those models at the earliest observable epochs. That is exactly what great science does. It does not validate what we already believe. It forces the questions we have not yet thought to ask. And every question Webb forces is itself a signal, not from a detector, not from a data set, but from the universe itself, to the minds studying it. A kind of message that reality sends to the creatures capable of measuring it. Your description is incomplete. Look again. Look deeper. The thing you are describing is larger than the description you have built for it. Science is, at its core, the practice of receiving and responding to that message. And right now, across gravitational wave astronomy, CMB cosmology, and deep galaxy observation simultaneously, the message is arriving from 3 different directions at once. Consider what it would mean if the pre-Big Bang hypothesis is true, not in its philosophical implications. Those are real and profound, but they are downstream of something more basic. Consider what it would mean physically. It would mean that the space-time geometry of our universe carries, encoded in its oldest observable features, information about a state of existence that preceded our universe entirely. Information that survived a transition so extreme, a contraction to near infinite density, or a complete evaporation of all matter into featureless radiation, that our current physics can barely describe it. That information did not travel to us through space. Space, as we know it, did not exist in anything like its current form at the moment that information was generated. That information did not travel to us through time in the ordinary sense. Time, as we experience it, may not have had the same structure or meaning on the other side of the bounce or the conformal transition. And yet, if some of these frameworks are correct, the information arrived, encoded in the geometry of space-time itself, in the lowest frequencies of the gravitational wave background, in the largest angular scales of the CMB, in the seeds that, through inflation, became the structure of everything we observe. The universe may not be carrying a signal from before the beginning. The universe itself may be the signal. A pattern continuing in matter and energy and space-time geometry. A pattern so deep it persisted through the most extreme transition physics can describe and re-expressed itself in the cosmos we inhabit. That is not a mystical idea. That is what some peer-reviewed theoretical physics, taken seriously and followed to its logical consequences, suggests is possible. The Big Bang in this reading was not a beginning. It was a memory. The universe repeating a pattern it could not quite escape, encoded in it from something older than itself. The 2030s will be a decade of extraordinary measurement. LISA will map the gravitational wave sky at frequencies no previous instrument has reached, probing epochs in cosmic history that have been inaccessible until now. CMBS-4 will map the polarization of the ancient light with sensitivity that may resolve the large angle anomalies into either a clear physical signal or unambiguous noise. LIGHT-BIRD will do the same from space. The Einstein telescope will open sensitivity windows across a wider frequency range than LIGO can reach, and Webb itself will continue building its catalogue of early galaxies, a catalogue that is already demanding revisions to the physics of the universe's first moments. None of these instruments was built to answer the question of what preceded the Big Bang, but all of them will generate data that the pre-Big Bang frameworks make specific, testable predictions about. All of them will either confirm that specific component of the signal, the one that cannot be accounted for by any process born inside our universe, or they will constrain it into non-existence, narrowing the space of what a previous universe could have been, or whether one existed at all. Both outcomes are science. Both advance the human understanding of where we came from. Both are worth the decades of engineering and observation and careful analysis that will produce them. And here is what matters most about the position we are in right now. This investigation has a shape. It is not a vague hope that better instruments will reveal something unexpected. It is a structured search with defined targets, defined frequency ranges, defined angular scales, defined polarization patterns, all derived from theoretical frameworks that make specific claims about what should be observable if a previous universe left any trace in this one. The search is not beginning. The search has already begun. The data exists. The anomalies are real. The gravitational wave background is confirmed. The early galaxies are in the catalogue. And the instruments that will push the question from suggestive to answered or genuinely constrained are being built right now. You have travelled an extraordinary distance tonight. From a faint smear of ancient light in Webb's data, a galaxy that should not have existed, to the deepest question physics has ever seriously entertained. We have crossed the CMB wall together and found gravitational waves passing through it. We have sat with 4 anomalies in the oldest image ever captured and felt the weight of their stubbornness. We have explored the mathematics of a bounce and the geometry of an infinite cycle and the silence at the edge of what any instrument will ever see. This is not a small thing to have held in mind. The question of what came before our universe is perhaps the most profound question a conscious being can ask. Not because it is unanswerable, but because it is now, for the first time in human history, scientifically answerable in principle. That shift from philosophy to measurement program happened in our lifetime. You are alive in the moment when that shift occurred. The data is wrong in a way that matters. That is where this began, with an instrument staring at one point in the sky for 10 hours, returning a number that the standard model could not quietly accommodate. And that wrongness, followed carefully and rigorously and without flinching, has led here to the genuine, structured, peer-reviewed possibility that the universe we inhabit is one chapter in something older than we can name. Whatever the answer turns out to be, whether the signal arrives in the 2030s or remains just beyond our instrument's reach for another generation, the question itself is one of the most remarkable things our species has ever asked, and asking it well, with real mathematics and real data and real humility about what we do not know, is perhaps the finest thing science does. The silence before the signal is still there. But we are listening now, and we know, at last, exactly what we are listening for. There is something worth saying before this ends, not about the data, not about the instruments, about you, sitting here in the quiet at whatever hour this found you. The universe spent 13.8 billion years producing the conditions for a mind capable of asking whether it existed before it began. Hydrogen collapsed into stars. Stars burned and died and scattered heavier atoms into space. Those atoms found each other across billions of years and billions of miles, and eventually, improbably, they became something that could sit in the dark and wonder about its own origin. That is you. Right now. Tonight. Webb did not begin this search. You did. The moment you asked the question, the moment you refused to accept that the beginning was simply the beginning, you became part of the only process in the known universe capable of finding the answer. That is not a small thing. That is perhaps the most extraordinary thing physics has ever produced. Thank you for making this entire journey with me. If tonight moves something in you, please subscribe to this channel and leave a like. It is how we keep searching together, and it means more than you know. The signal is still out there, and the fact that you are listening for it, that is the most human thing there is, because somewhere in the silence before the Big Bang, before time had a name, before space had a shape, something was happening, and 13 billion years later, in a quiet room, on an ordinary night, you cared enough to ask what it was. That matters. You matter, and the universe, in whatever form it has taken before ours, and whatever form it will take after, has never once produced anything quite like the mind that wonders about it. Good night, and thank you for sitting in the dark with me tonight and daring to ask what was there before the light.